So now that we have the DC value at 1.25 volts for V out, we can take this and plug it into our drain to source value in the current equation. So we've got 60 microamps for our drain current, which I've chosen, VDS of 1.25 volts, lambda, which you have found from part 1 of your lab, and the length 300 nanometers, overdrive voltage 0.1 volts. You've got your mu and Cox numbers, and you can calculate your width. So for this case, I'm going to assume that lambda is equal to 0.5 because I have not solved part 1 of your lab. You will not make this assumption. You will calculate the lambda of the NMOS device based on part 1. So you'll do that hand calculation. So I'm going to assume lambda of 0.5, and if I do that, I'm going to have 60 microamps, 1/2, 274.75 microamps per volt squared. The W, which is what I'm solving for, 300 nanometers, my length, 0.1 volts squared for the overdrive voltage, 1 plus lambda assumed of 0.5, again yours will be different, times 1.25 volts, and I can solve for the width, and I will have 7.18 microns. Now, this process technology only works in increments of every 150 nanometers, which is 0.15 microns. So I'm going to round this to the nearest 150. So I'm going to say round to W of 7.15 microns. And this will be the starting point for my width in my simulation, for my NMOS width. Okay, so the fourth part of your lab, you plug in this width, you have your biases for your VGP and VGN that we found in the first part of this analysis. You've got your VDD of 2.5 volts. I have a supply current that you would like to have, 60 microamps, which is what I've designed for. And you will do a sweep of the width of this PMOS. The length is staying at 300 nanometers. So in part 4, you actually do a simulation to find the width of this PMOS. So what are you looking for in that simulation? Well, you're looking for the case that gives you an I supply, or IED, whatever you want to call that, of 60 microamps, because that's what we initially designed for, and your V out DC voltage of 1.25 volts, because those are the design constraints that we placed on our analysis to find our width of our NMOS device. So we want our supply currents to be 60 microamps, or at least less than or equal to 60 microamps. It will be slightly different from this. They do not have to be exact. And we want our DC voltage to be sitting around 1.25 volts. So you're going to set your variable, WP, and then you're going to sweep it in simulation and find the width that gives you as close as possible to these numbers. Now again, the current can be less than 60 microamps. This actually may be a factor of 2 difference. So you may be getting 30 or 35 microamps when we've designed for 60, and that's actually pretty typical. But you want to definitely make sure that your DC voltage is sitting around the center point, 1.25 volts. Okay, so I will let you do part 4 and sweep that. You will find a width there through that simulation, and then you can continue from there and do the 5th part of your lab as well as the 6th section. In the 6th section, you find the small signal parameters GM and R0 using simulation. So you use your results browser to actually find R0 or R out of each device, R out P and R out N, and your GMs of each device, the NMOS and the PMOS. Note for your section 5 that you, or excuse me, section 6, that GMP will not equal GMN. They may be slight differences in simulation because this is a very accurate GM, right, where our hand analysis are approximations, and your R0P will not equal your R0N. Okay, in a lot of our analyses we assume the R0s are equal, but when you do your simulation for your 6th section, they will not be equal to each other. Okay. All right, so let's look at how all of this ties together, which is your section